All right, let's continue looking at state machine analysis. So I want to do one more example worked out completely from beginning to end. I want to use JK flip-flops, which are, the more complex flip-flop to analyze. And I want to just kind of go through these steps that we've been working with last time on how to go from the circuit design to ultimately a state diagram. Um, and then we'll talk a little bit about different types of outputs, what are called Mealy outputs and Moore outputs. And then we'll take a quick look at setup, hold times, propagation delays, and see how that can tell us the maximum speed for a state machine. And that will do it for this lecture. And then starting with the next lecture, we'll take the other direction and start trying to synthesize state machines from state diagrams. So I'm going to make a state machine with two JK flip-flops. And so as usual, I'll index these J0, K0, Q0, Q0 bar, J1, K1, Q1, Q1 bar. I'll indicate, that they're clock devices, but I won't show the clock. And I'm going to, make a fairly random circuit. So I am going to use two inputs this time. So I'll have X1, and let's say this gets ANDed with Q0, and that feeds K1. And let's take another input, X0, and just feed that directly into J1. And let's take Q1 and Q0 bar, and we will XOR these and send that into J0. And I don't know, I'll just take Q1 bar and send that into K0. So we got two flip-flops, two inputs, and then where should we take our output from? I'll take the output from right here. Well, actually, let's do something a little different. Let's take this and X1, and let's AND those. Let's OR those, and we'll call that output Z. Alright, so there's a fairly complex looking machine. And we're going to apply this set of steps to come up with a state diagram showing us how this system changes each time that the clock ticks. The clock, taking the inputs of the flip-flops, updating the outputs accordingly. So first question, how many flip-flops? 1, 2. 2 flip-flops. How many states? 4 states. Just 2 to the second power tells us how many states. So make a state name table. So I'm going to list the values of Q, Q1 and Q0, and there's 4 possibilities. And as before, I'll call these S00, S01, S10, and S11. All right, next step, write output equations. So what are the outputs here? Well, there's one output, Z, and Z is just equal to X ORed with Q0 bar. Next step, write equations for the flip-flop inputs. So a JK flip-flop has 2 inputs, J and K, right? We don't count the clock as an input, so we're just looking for equations for J0, K0, J1, and K1. And we just write these from the circuit diagram. So what feeds J0? Well, it's coming out of an XOR gate. And the 2 inputs are Q0 bar and Q1. So J0 is Q0 bar XORed Q1. K0 looks like it just comes from Q1 bar. J1 just comes from X0, which is an input, and K1 comes from an AND of X1 with Q0. This was an X1 up here. So X1 ANDed with Q0. that gives us K1. Alright, so we've got the equations for flip-flop inputs. We're ready to make a state transition table. So we don't need the diagram anymore. We know what the state names are by habit, so let's just go ahead and use these equations and fill in a state transition table. So we're going to start off with present state. And inputs, in our inputs we have two inputs, x1 and x0. Alright, so there's 16 possibilities. We could be in state S00, and our inputs could be 0, 0, 0, 1, 1, 0, or 1, 1. We could be in state S01, and our inputs could be 0, 0, 0, 1, 1, 0, or 1, 1, and so on. We could be in state S10 with any of those four combinations of x1 and x0, or we could be in state S11 with any of those combinations of x1 and x0. So there's our set of present state and input combinations. And then we're going to add a column for the Q's corresponding to this present state. So I'm going to list Q1, Q0. And I can just read this directly from the state. In these four cases, it's 0, 0, here's 0, 1, here's 1, 0, and here's 1, 1. Alright, so we can ignore the names for now. We basically have 16 rows, each showing a pair of x values and a pair of q values. And using that and these equations, we can fill in all of this information. So the next thing we fill in is the outputs. Well, we have a single output z. And z is just x1 ORed with q0 bar. Now normally I would say write a column for q0 bar and then fill in the OR, but I'm going to skip a bit. I'm going to do a few of the steps in my head, right? I'm going to say, okay, where is z a 1? Well, it's a 1 anytime that x1 is a 1. So that's these rows. Because x1 is a 1, z is going to be a 1. But also anytime that q0 is a 0, z will be a 1. So q0 is a 0, q0 is a 0. And then in all the other situations, z is going to be a 0. For example, here, q0 is a 1, x1 is a 0, so x1 ORed with q0 bar is a 0. Alright, so now we're going to fill in our other inputs to the flip-flops. And the order is going to be helpful here, right? JK flip-flops. We're used to looking at the behavior, or will be used to looking at the behavior as J followed by K. So I want to list J before K. And as with everything else in this table, I'm going to do subscript 1 before subscript 0. So first I'm going to do J1, and that's just a copy of X0. So 0, 1, 0, 1, all the way down. And then K1 is X1 ANDed with Q0. So anywhere that X1 is a 1 and Q0 is a 1, K1 is going to be a 1. So I'm looking for 1s in these two columns. And it looks like here and here I've got a pair of 1s. And then I've got 0s, 1, 0, 0, 1s. But here and here I've got a pair of 1s. And then everywhere else it's going to be a 0. So you should fill out, these columns in whatever way is methodical for you, including, perhaps, copying values over or highlighting them or, blocking them off with paper so that you're only looking at the variables that you're interested in. But you have to do this very, very carefully. If you get the wrong values here, your system diagram will not be what it should be. All right, so that's J1, K1. Let's look at J0. And J0 is an XOR. And it's an XOR between Q0 bar and Q1. All right, so an XOR says exactly one of these should be a 1 and the other one should be a 0. So I'm going to look at the complement of Q0. So this is a 1, 0. That XORs to a 1. Here, Q1 will be a 1, Q0 bar, sorry, Q1 will be a 0, Q0 bar will be a 0. So this would be 0 XORed with 0. These are all going to be 0. Here, Q0 bar is a 1, Q1 is a 1, and 1 XORed with 1 is a 0, because an XOR you can only have one input being a 1. And here, Q0 bar is a 0, Q1 is a 1, 0 XORed with 1 is a 1. So that's J0. And finally, K0 is just the complement of Q1. It's just Q1 bar. So I can just copy this Q1 column and flip my bits. Alright, so there's the inputs to the flip-flops. Now for the flip-flop analysis, we want to figure out what the next state is in terms of Qs. So I'm going to say next state Q1. Alright, so we have to analyze the JK flip-flop and say if J is 1 and K is 1 and the current value of Q1 is 0, what happens when the clock ticks? So let's remember what a JK flip-flop looks like. Right? If J and K are 0, Q doesn't change. JK 0, 1, Q becomes low. JK 1, 0, Q becomes high. JK 1, 1, Q becomes the opposite of what it is. So anywhere that J and K are zeros, Q is going to be unchanged. So 0, 0, Q1 is a 1, it's going to stay a 1. And in all four of these cases, J and K are 0, so Q1 is going to stay unchanged. It's just going to be a 0. Alright, it turns out, it doesn't always work out like this, but it turns out all four of these have the same JK. And I'm looking at the wrong set of inputs. So let's look at the correct inputs, J1, K1. So if J1, K1 are both 0, Q1 does not change. So let's find all the places where J1, K1 are 0. There's a case here, so Q1 will not change. There's a 0, 0, so Q1 won't change. There's another 0, 0, so Q1 won't change. Well, right here, Q1 is a 1, so it will stay a 1. There's a 0, 0, Q1 stays a 1. There's a 0, 0, Q1 stays a 1. And that's it. All right, now in the second row, J is a 1, K is a 0. And if J is 1, K is 0, the flip-flop goes high. So anytime we see a 1, 0, we know the new value of Q is a 1. So right here, right here, right here, right here. All right, when we have a 0, 1 for J and K, the new value of the flip-flop is 0. So J and K are 0, 1, new value is 0, 0, 1, new value is 0. And the last case is when J and K are both 1, the flip-flop should toggle. So J and K are both 1. The current value of Q1 is 0. After the clock ticks, it'll toggle to a 1. Here J and K inputs are 1. The current value of Q1 is 1. After the clock ticks, it'll toggle to a 0. Alright, and now we can fill in Q0, and for Q0 we look at J0, K0, and Q0. So J and K are 1, 1. That means that the value of Q0 is going to toggle. Well, in all four cases, Q0 is a 0, so it's going to become a 1. Here, J is 0, K is 1. That's the reset condition, so it doesn't matter what the current value of Q is. The new value is going to be 0. Here's a 0, 0, which means leave Q unchanged. So in all four of these cases, Q is a 0, so the new value will be 0. And here's a 1, 0, which says set the flip-flop, so the new value of Q will be 1. And now we can fill in our last column, which is the name of the new state. And this is S01, S11, S01. And we can just copy these down. You know, we could go to our state assignment table and say, oh, Q1's a 1, Q0 is a 0, 1, 0, that's state S10. I don't have to do that because, again, I have a habit of naming my states based on this particular ordering of the flip-flops. So it looks like S10 is a very popular state. And there's our state transition table. And with this information, we can complete our last step, which is to make the state diagram. And so I'll list 4 states. And if we take a look at our outputs, we can see that in some cases our output is determined completely by our state. If we're in state S10, our output is always 1. But in some cases it depends not only on the state but also on the input values. So I'm going to make a key for my diagram, which says I'm going to put the name of the state inside a circle. I'm going to draw a transition arrow, and on this arrow I'm going to list my 2 inputs, x1, x0, followed by a slash, followed by the output value. And we're going to have 4 arrows coming from each state, because for each state we have 4 possible combinations of inputs. Alright, if we're in state 0, 0, and our inputs are both 0, we're going to go to state 0, 1. So this is the transition with input 0, 0, and if our input is 0, 0 and state 0, our output is a 1. If our input is 0, 1, we're going to go to state S11. So input of 0, 1 takes us to this state, and our output there is also a 1. If our input is 1, 0, we go to 0, 1. So here's 1, 0, and in that case our output is still 1. And if our input is 1, 1, we're going to go to state 1, 1. So if our input is 1, 1, we go to state 1, 1, and in that case our output is a 1. And don't get confused, right? Our output is based on the current state. The way to think of this is if right now we're in state 0, 0, and we set our inputs to this, our output's going to be 1. Right? If we're in state 0, 0, and our input is 0, 1, our output's going to be 1. Now after the clock ticks, right, we might be in a different state and we might change the output, but we're looking at when we're in this state and this is our input, what is our output? Alright, so there's 4 of our arrows. Let's continue. If we're in state 0, 1 and we have a 0, 0, our new state is 0, 0, output is 0. So this is where we go with an input of 0, 0 and our output is 0. If our input's 0, 1, we go down to state 1, 0, and our output is 0. So 0, 1 with an output of 0. If our input is 1, 0, we also go to 0, 0. And in that case, our output is a 1. And if our input is 1, 1, we go to 1, 0 with an output of 1. So if we're 1, 1, we output 1, we go to state 1, 0. All right, halfway done. If we're in state 1, 0, state 2, we go to state 1, 0. It looks like state 1, 0 always goes to state 1, 0. So that's kind of convenient. It looks like the output is always 1. So I'm going to go ahead and draw all 4 situations. And again, whatever our input is, the output is 1. Our new state is 1, 0. So 0, 0 outputs 1, 0, 1 outputs 1, 1, 0 outputs 1, 1, 1 outputs 1. Now you may be tempted to use wildcards to put a dash in here. Don't do that, right? If we need to do that, we'll make it very clear that that's allowed to be done. But it's really important that you do this the same, even if you can see a shortcut way of writing it. Because when we're done, we want to make sure we have 16 arrows, right? And wildcards will change that. All right, so our last 4 situations were in state S11, and it looks like these 2 inputs output a 0 and go to state S11. So let's fill those in. So if our input is 0, 0, our output is 0, and we go to S11. If our input is 0, 1, our output is 0, and we go to S11. And then it looks like the last 2 situations, we go to state S01, and our output is a 1. So we've got 2 more transitions here. This is a 1, 0, output a 1. And this is a 1, 1, output a 1. And there we go. There's the complete analysis of our state machine. So we started with just this diagram, and we transformed it into this picture. And so from this picture, we can see a little more clearly what's going on. For example, we can see once you get into state 1, 0, you're stuck, right? Your output is always going to be 1, and no matter what happens, no matter how many times you tick the clock, you're always going to stay in this stage. So this is some kind of terminal stage. If you're in S1, you could stay in that state indefinitely for certain input values, or you could go to state 2. Sorry, state 1. Those are your only options. Either stay here or go here. If you're in state 1, you're going to go to state 0, and if you're in state 0, you're going to go to state 1 or state 3. And state 1, you can ping back and forth to 0, or you could go to 2. So your only way to get to this state 2 is through state 1. And any of your states, 0 or 3, can take you to state 1. So we could start, looking at ways that you can move from one state to another. How do you get to this terminal state? Or can you continually change states without going to this terminal state? Now, if this was not a completely random circuit, there might be some, rhyme or reason to this diagram. For example, one of these inputs might be a halt input that forces you into this state, and another one might be a hold input that leaves you, in a pair of states or something. But this was just a made-up example. But anyway, that's the analysis process. So with that, we can take any circuit diagram and apply those steps and come up with a state diagram that shows us, how the circuit behaves. All right. So 2 things I want to dig into a little further. The first is a closer look at outputs. And in this case, we had a single output Z, and it depended not only on the state you were in, but also on the value of the inputs. In other words, if you're in state 1, you can't say whether your output is 0 or 1 unless you also look at the values of the inputs. And if my inputs are 0, 1, my output's low. If my input is 1, 1, my output is high. So we need this additional information in order to understand um, what the outputs are going to look like. So there's two situations here. Um, Situation one, if an output depends only on the state, this is called a Moore output. And generally when we draw a picture, we would list the name of the state, and then we could show what the output value would be for that state. But in some cases, like the example that we just did, an output also depends on an input value. This is called a Mealy output. And in that case, on the transition arrow, we list the input and a slash and the output. And in our key, we indicate what those variables are. And it's possible a machine could have a combination. There could be one output that's only based on state. That would be a Moore output, and we could put it in the state circle. But there might be another output that depends on the input value, and we would list that on the transition arrow as a Mealy output. Now, what's the significance of this? Why do we have separate names for these? Well, there's a fundamental difference in the behavior of a Moore machine versus the Mealy machine. A Moore machine is absolutely stable in between clock ticks, right? Until a clock ticks, you don't change state, and based on whatever state you're in, the outputs are predetermined. But a Mealy machine, even between clock ticks, if an input changes, it could change the output coming from the machine. So a Mealy machine can change outputs in between clock ticks. A Moore machine will only change outputs when the clock ticks. So that's kind of a fundamental difference in behavior. It's not super significant though, because it turns out we can take a Mealy machine and turn it into a Moore, and vice versa. We can turn a Moore machine into a Mealy. We can think of one as being the other, so it's not like an inherent limitation, but it's going to affect what our state diagram looks like. In this case, Z was a Mealy output, and so we listed it on the transition arrow next to the inputs. All right, so last thing I want to talk about is clock speed. And clock speed is, we touched on this before when we started looking at flip-flops, but here's a better example. Suppose that we go back to our original drawing where we had some memory, and then in this case, we've got 4 outputs going into some combinational logic, and this generates some outputs, one output in this case, and there's some inputs coming into this machine, and then there's a feedback path. And in this case, there's 4 lines of feedback coming into these flip-flops because we have 4 inputs. And we want to know what's the maximum clock speed. Well, if we know the propagation delay of each of these gates, we can figure out what the worst case propagation delay is. And even though looking at this, we see, 3 logic gates, if X or Q changes, we basically have to go through an AND gate to set up this input. If Q0 bar or Q1 changes, we go through an XOR gate to set up this input. And this doesn't feed back into our circuit. This really just affects the output Z. And so if we found the propagation delay was, 10 seconds and 20 seconds and, 7 nanoseconds, We could actually, say, okay, worst case is going to be the propagation delay through this gate. But you do some kind of calculation. If you do this with software tools, one thing it will tell you is, what's the worst case propagation delay from an input change to an output, and it'll come up with some figure for you, and it's going to be an over approximation, because if you come up with a number that's higher than reality, that's okay. But if it might take 20 nanoseconds to come through this circuit and you decide the worst case is 15, then you've got a design problem. So let's suppose that the propagation delay is 20 nanoseconds. No reason that would be true, I'm just supposing it. And let's suppose that our flip-flops have a setup time of 30 nanoseconds and a hold time of 15 nanoseconds. What's the maximum clock speed for this circuit? And basically the situation is, once the clock ticks, you're going to get new outputs from your flip-flops. Those are going to go into your combinational logic, filter through whatever logic gates you have, generate outputs. Those outputs will set the inputs of your flip-flops. All right, so clock ticks. "20 nanoseconds later, CL outputs, which are the same as the flip-flop inputs, are set." Right, worst case 20 nanoseconds. The setup time on our flip-flops say, hey, once those inputs are stable, you still have to wait this long before you can tick the clock. So 30 nanoseconds later, safe to tick the clock. The hold time usually doesn't matter. The hold time says we have to keep those inputs stable for 15 nanoseconds. Well, once we tick the clock, it's going to take 20 nanoseconds for these changes to propagate through. And usually the hold time is dwarfed by the amount of time required for the combinational logic. So we're going to ignore the hold time. We're going to basically say, hey, 50 nanoseconds, safe to tick the clock again. So here's what our timing diagram looks like. Here's the clock tick, right? 20 nanoseconds later, combinational logic is set up. 30 nanoseconds later, the inputs to the flip-flop have been stable for the required setup time, and now we can tick the clock again. Right, so this is 20 nanoseconds for the outputs to be stable, 30 nanoseconds for the setup to occur. That's a total of 50 nanoseconds. So minimum period, time between ticks, is 50 nanoseconds. So the reciprocal gives us the maximum frequency, is 1 over 50 nanoseconds. Well, what is that in seconds? So let's do a cleaner calculation here. So 50 nanoseconds per tick. So that's 50 over 10 to the 9th seconds per tick. If we take the reciprocal of that, we get 1 billion ticks every 50 seconds. So what's 10 to the 9th divided by 50? That's 10 to the 8th divided by 5, which is 2 times 10 to the 7th, which is 20 million ticks per second, which is 20 megahertz. So maximum clock speed for this circuit, 20 megahertz. assuming, you know, a setup time of 30 and a propagation delay of 20. So not all that fast, right? So how do we build a machine that can run at, you know, gigahertz speed? Well, it's a really hard thing to do. And we can't do it with these chips that we find on engrcs.com. We need chips with, you know, sub-nanosecond setup times, propagation delays, and so on. And it's just a matter of using very, very small devices with very low voltages, so you don't have to swing a voltage all the way from 0 volts to 5 volts. We swing it maybe from 0 volts to, you know, 0.5 volts, and maybe that registers as a logic 1. And very low power, right? Not enough power to drive an LED, not enough power to raise the voltage on a big pin coming out of a chip, but just a little tiny bit of current, right? Small number of electrons, because we're going through a wire that is, you know, a few angstroms across perhaps. This is why integrated circuits run so much faster than circuits built out of discrete components. All right, so that's a maximum clock speed example, right? We basically do that analysis. We find 50 nanoseconds, 20 megahertz. All right, so next class we will begin looking at the reverse process. We'll start with a diagram like this and figure out how we work our way to a circuit that will achieve this behavior. So that'll be the synthesis part.